Hey space friend, it's been a few years since I stole this ship and I realized today that I still don't have a proper navigation system or signal scanner. Today we're going to use a joystick, rotary encoder, and OLED display to better navigate the cosmos and scan for signals. Frequency is basically how fast a wave repeats. Radios work by tuning into specific frequencies, so this scanner simulates sweeping through different signal bands searching for a transmission. Electrical signals can oscillate in repeating waves, where voltage moves up and down like high, low, high, low, high, low, repeating over and over. The speed of that repetition is the frequency. Sound is a vibration. Low frequency sounds are things like bass, rumbling, or deep voices because the vibrations repeat more slowly. High frequency sounds are things like whistles, birds, or high-pitched tones because the vibrations repeat much faster. In sound waves, the air itself compresses and expands, pushing back and forth through the air. That's how speakers create sound and how our ears detect it. Electrical signals in radio waves also involve repeating oscillations, but instead of moving air, they involve changing electric and magnetic fields. Just like sound, they can oscillate slowly or quickly, meaning they also have frequencies. So when we tune the rotary encoder in this project, we're simulating scanning through different frequencies the same way a radio receiver searches through different signal bands looking for a transmission. As you rotate the encoder through empty frequencies, the system mostly detects random background noise and interference. But when the scanner reaches the correct frequency range, the signal suddenly becomes much stronger and clearer. This is similar to how real radios work. A radio receiver tunes into a specific frequency band and filters out most other signals. When the receiver matches the frequency of the transmitter, it can isolate and decode that transmission from the surrounding noise. In our project, the Arduino simulates this by comparing the selected frequency against a hidden target frequency within the code. The closer we get to the correct frequency, the stronger the detected signal will become. The first few things we're doing are setting up our OLED display, joystick, and rotary encoder pins. I'll include links at the end of this video and in the description if you want more information on those things to learn more about how they work. Cursor X is the horizontal position of the cursor on the OLED, and cursor Y is the vertical position. Zoom level is where we're starting the zoom at that we'll be able to change when we turn the encoder. Scan frequency is the currently selected frequency that the scanner is on. This is just a random number choice. 140 doesn't mean anything. The modes are whether the rotary encoder is in star map mode or signal scan mode. Next, we're declaring the variable last clock state, which is holding space in memory for the last state that we'll assign to it later in the setup. The timing variables store a placeholder value of 0 to the last move and update and assign a delay to the joystick and the OLED. Without using the screen update delay variable, the Arduino would redraw the screen thousands of times per second over and over, which would waste performance or cause flickering or slow the program down potentially. So here we're creating variables to create a simple timer system that will store how long to wait between screen redraws, which is measured in milliseconds. In the setup, which will only run once, we are going to start the serial monitor and set the pins up for the joystick and the encoder. Then we use the last clock state variable to read the state of the encoder. We start the OLED display, set a random seed for the random function to start at using a floating pin, which is why we're using A2 that's not connected to anything. Then we call the boot screen and the draw screen functions that we'll define later. In the loop, which runs continuously, we call functions to read the state of the joystick, encoder, and the encoder button. In this if statement, millis is a built-in Arduino function that returns how many milliseconds have passed since the Arduino was turned on. Immediately is 0, 1 second is 1,000, and so on. So if the Arduino turned on 3 seconds ago, millis would store the value 3,000. Let's say that's the current time and the previous update in last screen update is 2800. Millis minus last screen update calculates to 200, so the elapsed time means 200 milliseconds have passed since the last screen update. Then the greater sign checks if that time is more than the delay variable we set to 100. It is in this example, so enough time has passed, so then the Arduino can go ahead and redraw the screen. It then updates the last screen update and calls the draw screen function. The boot screen function just prints text to the OLED whenever we call it. The read joystick function acts similarly to the previous if statement that we talked about. Return means stop running this function immediately and go back to wherever the function was called from. So the joystick is only updating for the amount of milliseconds stored in joystick move delay. If we didn't calculate the time and then put return to stop the function depending on that time, the cursor would just move way too fast. Within this function, we also set variables to read the joystick and for low and high dead zone thresholds. These thresholds are defining whether the joystick is close enough to the center so that in the next if statement, if the mode is set to star navigation, you have to push the joystick far enough off center for it to actually register that you're moving the cursor. This is important because joysticks are analog devices that don't stay perfectly stable 100% of the time, even when they're being untouched. The mode equals 0 if statement is how we move the cursor around on the OLED using the joystick. Constrain is a built-in Arduino function that constrains values to a minimum and a maximum range. The format is value, minimum, maximum. We're using it here to keep the cursor within the bounds of the star map that we drew. The read encoder function sets the current clock state variable to read the clock pin of the encoder. If the current state doesn't equal the last state and the encoder's data pin does not equal the current clock state, then call the encoder turned clockwise function, otherwise call the encoder turned counterclockwise function. Then reset the last clock state to the current clock state. The encoder turned clockwise and encoder turned counterclockwise functions are how we simulate zooming in and out of the star map. If the mode is 0, increase or decrease the zoom levels but constrain the values, and if the mode is 1 for the scanner, increase or decrease the scan frequency and constrain the values. The read encoder button sets a static Boolean variable of false to was pressed. Static means keep this variable's value between function calls. We need this because if the next if statement stating if is pressed and isn't was pressed needs to detect whether the button was pressed in the last loop. So if the button was pressed, we increase the mode by 1, and then if we press the button again, mode goes back to 0 because we're saying if mode is greater than 1, then it equals 0. Was pressed then becomes is pressed. The draw screen function calls draw star map if the mode is 0, otherwise calls draw signal scanner. The draw star map function is how we display text and colors to the screen. The draw zoomed star function takes 3 arguments, an integer for base x, an integer for base y, and a float for scale. So when we call this function here for the first time, the original star position is 12 horizontally and 18 vertically, and we're using the current zoom scale. The function then defines the map's center of 48 for x and 37 for y. Then we calculate the horizontal distance from the center with base x minus center x. So since base x starts at 12 and center x starts at 48, we get minus 36, which means move the star 36 pixels left of center. Negative means left and up, and positive means right and down. Then we multiply by scale to apply the zoom scaling. The if zoomed x is greater than 1 if statement is the final boundary check, so that if the star is outside our drawn boundary, then don't draw it. The draw digital scanner function prints text and color to the OLED, sets signal strength to calculate signal strength, and prints various things depending on what the signal strength is. To calculate signal strength, we set a random target frequency and take the absolute value of the difference in the scan frequency versus the target frequency. The target frequency is just a random number that I'm setting that we're going to lock onto. And then the strength variable maps and constrains values to the distance from target variable. Adding random noise makes the signal strength fluctuate instead of just being static and looking too perfect. The random function takes a minimum and maximum, where the minimum is inclusive and the maximum is exclusive, so this is constraining it to -8 to 8. Then we add strength and noise and constrain strength to 0 to 100 so that it doesn't go over 100% once we add in the noise. Let's test both of these out. Ooh, we've locked onto an anomaly signal. Okay, so the navigation console is operational, the signal is real, and I'm going to make the incredibly responsible decision to immediately go towards it.